Welcome to the Explainer. We hear these massive buzzwords thrown around literally every single day. LMMs, transformers, parameters, token limits. But today, we're moving way past the acronyms. We're going to pop the hood and look at the physical anatomy of modern AI models to understand exactly how these engines are actually built and what makes them run. So here's our roadmap for this Explainer. 1, we'll map out the architecture family tree. 2, we'll look at attention, the Transformer's secret weapon. 3, we dive into diffusion, denoising into art. 4, we'll decode those crazy model size metrics. And 5, we'll wrap up with quantization and context windows. Section 1, the architecture family tree, mapping the AI engine room. Before we get completely lost in the weeds with specific models, we really need to ground ourselves with a simple definition. What do we actually mean when we say architecture? Well, at its core, an architecture is simply the shape of a neural network. It defines what is connected to what. It's basically the wiring diagram of the artificial brain. The evolutionary leap in this field is just absolutely wild. Back in the day, we had early legacy models like the multi-layer perceptron, or MLP, which was mostly used for basic tabular data. Then came CNNs and VAEs, pioneering early image processing. But today, we have massive modern replacements. Transformers have completely taken over for text and audio, while diffusion models dominate image generation. It's this massive, fundamental shift from older sequential processing to the parallel processing powerhouses of today. Let's look at sequence processing, because the contrast here is brilliant. Legacy recurrent neural networks, or RNNs, and honestly, even their patched-up cousins like LSTMs and GRUs, they read data step by step, word by word. Because of that, they're notoriously prone to forgetting earlier parts of a sequence. But then, on the flip side, we have these highly promising experimental state space models like Mamba. These are built as faster alternatives to modern attention models, specifically designed to handle massive, ridiculously long context sequences efficiently without dropping the ball. Section 2. Attention, the Transformer's secret, and the magic behind modern text models. Okay, so the defining mechanism of the current era is something called attention. It's the fuel injection system of the Transformer, which has utterly dominated the space since around 2017. For every single word, piece, or token, the model essentially asks, hey, which other tokens are most relevant to me right now? Think of it exactly like a crowded cocktail party. A word walks in and shouts a query across the room. It then scans for matching keys held by other words. It mathematically compares these, and when it finds the best matches, it extracts the value or the context from them. This lets the model process all the positions in a sequence at exactly the same time, which GPUs absolutely love. And because they love parallel processing, the model runs this cocktail party simultaneously across dozens of different tables. We call that multi-head attention. Now, the crucial point here is that this attention mechanism comes in a couple of very distinct flavors. Models can look within their own sentence, which we call self-attention. This is literally how an LLM understands the grammar and the relationship of words inside a single prompt you give it. But they can also use cross-attention. This is where tokens in one sequence cross-reference an entirely different data stream. For example, an encoder-decoder model matching the pixels of an image directly to the words in a text caption. But there's a catch, right? Because attention processes everything simultaneously and parallel, it inherently has zero concept of order. The model literally wouldn't know if a word was at the beginning or the end of your sentence. To fix this, we use positional encoding. The gold standard today is ROPE, or rotary position embeddings. Think of these as little mathematical timestamps injected directly into the data. This guarantees the model never loses the actual sequential order of your words, even while it's calculating them all at exactly the same time. Pretty clever, right? Section 3. Diffusion, denoising into art, the visual AI engine. Shifting gears from text to visual art, we run into a completely different architecture. This is the engine powering almost all modern image and video generation tools right now. The core intuition of diffusion is actually beautiful. Imagine the model as a sculptor chipping away at a block of static. During training, it learns by taking a perfectly clean image and incrementally adding noise until it's just pure, unrecognizable static, learning how to reverse every single step. So at generation time, it starts with pure random noise and iteratively denoises it. It mathematically chisels away the static to reveal the art hidden beneath, heavily conditioned by whatever text prompt you typed in. Now, early models tried doing this directly on raw pixels, which, as you can imagine, is incredibly expensive computationally. Modern models, however, use latent diffusion. Instead of raw pixels, latent diffusion operates in a heavily compressed mathematical space, which makes processing drastically cheaper and way faster. This methodology has completely crushed older competing architectures, like GANs, simply because diffusion provides significantly better training stability and is much, much easier to steer with your text prompts. Section 4. Decoding Model Size Metrics. Understanding the hardware reality. Let's zoom back out from the algorithms and look at the vehicle specs. We hear these crazy numbers, but what do they actually mean for deployment? You might see a staggering number like 1.6 trillion total parameters for a frontier model, like DeepSeek V4. A parameter is essentially just a single floating point number, a weight, or a bias learned during training. This 1.6 trillion figure represents the model's overarching massive knowledge base, and it dictates the immense amount of physical memory required just to load the model into a server. But here is the truly shocking metric: 49 billion. This is the number of active parameters. Out of the trillions of pieces of knowledge the model holds, only 49 billion are actually active and firing to compute any single token. That is a massive reduction, drastically cutting the computing cost of running the model. So how is a drop like that even possible? Well, this clever little cheat code is known as a mixture of experts, or MoE. In an MoE architecture, the network is divided into many distinct specialist submodels. For any given word or prompt, only the relevant experts are activated. This lets frontier models boast trillion-parameter knowledge bases, while only actually paying the computing cost of a much smaller 40 or 50 billion parameter network at inference time. It's a total game changer. Section 5. Quantization and context windows, or how we fit AI on your laptop. We know how the models work, but how do we squeeze these absolute giants onto consumer hardware? This brings us to quantization. You can think of quantization exactly like saving a massive high-resolution raw image file as a smaller JPEG to save hard drive space. It deliberately reduces the mathematical precision of the weights. A 70 billion parameter model stored at standard 16-bit precision needs a massive 140 gigabytes of memory. But if you crush it down to 4-bit quantization, it only needs 35 gigabytes. Suddenly, that massive cutting-edge AI can fit comfortably and run locally right on a high-end consumer GPU. Finally, we have to talk about the context window. If parameters represent the model's lifelong knowledge, the context window is its active, short-term memory. Modern models can have context windows up to 1 million tokens. However, this active memory has strict limits. This perfectly explains why an AI might suddenly forget a specific formatting instruction you gave it 10 prompts ago. Past a certain point, usually around 200,000 tokens, performance begins to degrade, and these models are absolutely notorious for getting lost and forgetting the middle chunks of very long inputs. So let's tie this all together. Parameters are the ultimate knowledge base. The context window is the active working memory, and quantization is the cost trade-off we make to fit all of this power onto our desks. We've explored the engine room of today, which is beautifully dominated by Transformers and Diffusion models. But as computing scaling limits inevitably begin to approach, we have to ask ourselves, what entirely new, unimagined architecture is waiting in the wings right now, ready to completely rewrite this field guide tomorrow? Thank you for joining this explainer. Keep learning and keep building.